When we think about DNA, our minds usually jump straight to chemistry, right? We picture this complex molecule carrying all our biological instructions. But what if there's another way to look at it? A completely different way. This explainer is all about the groundbreaking research of Victoria Kayser-Cuny, who looks at the genetic code not just as chemistry, but as this profoundly mathematical structure.
And that one sentence, that really captures the entire shift in thinking here. Instead of getting lost in the weeds of biochemical reactions, this approach zooms out. It treats the code like an ordered, logical system and starts hunting for the rules and patterns that are hidden right there in its architecture. All right, so here's how we're going to break this all down. First, we'll look at this new lens on DNA. Then we'll get into the core calculation itself, the engine behind this whole thing. After that, we'll see the absolutely incredible patterns it reveals, explore the code's hidden geometry, and finally, see how this all points to it being a self-generating system.
Okay, so let's get started. Let's put on this new set of glasses and take a look at our own genetic blueprint in a way you've probably never seen before. So, on the left, you've got the classical way of thinking. DNA's function is all about its chemical interactions. But Kayser-Cuny's approach, over on the right, does something different. It doesn't throw out the chemistry. Instead, it acts like a mathematical magnifying glass. It applies a formula to the atoms themselves to show us patterns that were there the whole time, just hiding in plain sight.
So what is this magnifying glass? I mean, how do you even begin to translate the building blocks of life into pure numbers? Well, it all boils down to one core calculation.
The whole thing is built on this concept called the theoretical codonic unit, or TCU. The easiest way to think about it is as a kind of logical mass. It's basically a number that gets assigned to each piece of the code, and that number comes directly from the subatomic particles of its atoms.
So the first step is actually pretty straightforward, but really powerful. For every single atom involved, carbon, hydrogen, nitrogen, oxygen, you just multiply its number of protons by its neutrons and then by its electrons. This product gives each atom its own unique numerical signature.
Then that value gets transformed. You take it, you cube it, and then, and this is super important, you divide it by 4. Now, that's not just some random number. Dividing by 4 is key because it tunes the whole system to the fundamental 4-part structure of the code itself. We're talking 4 main atoms, 4 nitrogenous bases, it all clicks into place. Okay, now this is where things get truly mind-bending. When you take this calculation and you apply it to every single part of the genetic code, from individual atoms to whole codons, something amazing happens. These astonishingly consistent patterns just start to pop out. And this table here illustrates one of those patterns perfectly. When you run the numbers, you find these consistent numerical jumps, or what we call invariants. Take the number 128, for example. It shows up as this key interval when you move between major groups at the atomic level, at the base level, and even at the full codon level. It's the same pattern repeating at every single scale. It's wild.
So these repeating patterns, these invariants, they mainly come in 3 flavors. The first one is the number 1. It pops up over and over again, marking the smallest, most fundamental steps you can take within different families of codons. It's like the system's most basic unit of change.
The second key invariant we see is a value that always hovers right around 96. And this number acts like a standard unit of measurement, consistently marking the numerical distance between different families within the code. And finally, we have the third and probably the most important invariant, 128. As we just saw, this number is like a universal signpost. It marks the major transition between the biggest groups at every single level of the code's organization. It's everywhere.
But here's the thing. These numbers aren't just a random list of fun facts. The way they're organized reveals this deep, almost geometric structure hiding underneath it all.
When you plot out all the TCU values you've calculated, they don't just scatter randomly. They naturally sort themselves into 4 main groups, or packets. And right away, that suggests this isn't some chaotic mix of numbers. It's an ordered, layered system.
But it gets even crazier. Look at how many values are in each packet. The first one has 9, the second has 6, the third has 3, and the last packet has just 1. I mean, come on. That clean 9631 pattern is a massive clue screaming at us that this arrangement is anything but random.
And that sequence isn't just tidy,
It's mathematically profound. It follows the logic of what are called triangular numbers, and it's a mirror image of the kind of combinatorial structure you find in something as fundamental as Pascal's triangle. We are literally seeing basic mathematical laws emerge straight from the atomic structure of our DNA.
And the connections go even deeper than that. This shows a jaw-dropping parallel between the code structure and the electronic structure of atoms and particle physics. The packets of 1, 3, and 6 elements perfectly mirror the s and p subshells that hold electrons. It's this potentially huge link between the logic of life and the fundamental laws of physics.
So, this brings us to what might be the most powerful part of this whole model. Its ability to not just describe what's there, but to actually predict what should be there.
Remember that first packet, the one with 9 values? Well, it's special. It acts as a generator. Think of these 9 numbers as the core seeds. They're the essential building blocks from which the rest of the entire system can be built.
And here's how it works. You can take a value from that core generator set, do a simple operation on it, like just doubling it, and boom, the result is another significant value that already exists somewhere else in the code. The system is literally building itself from its own basic parts. It's completely self-referential.
And this is the real kicker, right? It's one thing to find cool patterns in data you already have, but the true test of any scientific theory is whether it can predict something new. And this model was used to predict the numerical values for a more complex, hypothetical 4-base code, and its predictions were spot on, exact.
Which brings us to the final, really profound takeaway from all this. The code. Well, it appears to be fractal. You know, like a fern, where each little leaf is a tiny version of the whole branch? Or a snowflake with its infinitely repeating patterns? It's the same idea. The same organizational principle, the same internal geometry, just repeats itself at every single scale, from the atom all the way up.
So we're left with this final, really provocative question. If the blueprint for all life isn't just some messy chemical soup, but is instead a system built on such a precise, elegant, and self-generating mathematical foundation, what does that really tell us about the nature of life itself and the universe it calls home?